The outline basically of my talk today, that I will talk about the initial discovery of metal composites, the global market and recent trends in metal matrix composites, the effect of microstructure, property motivation, why do we use metal composites, and how they can save energy and reduce pollution, very much in line with the 20th year objective of sustainable and green world of the IAAM. Then I will share with you some of the components of metal matrix composites that are currently in use, including some components that we have developed, and then conclude my talk with some research imperatives as I see things that can be done by people in the future. So this is the kind of a slide of the original discovery with my colleague. This is myself, Frank Vedia, and what we had done for the first time, introduced nickel-coated graphite particles in aluminum and solidified the melt. And this was published in 1969, about 50 years ago. And we produced a microstructure where these black graphite particles are dispersed in the matrix of aluminum. So this was the first example of synthetically produced cast metal matrix composite between two immiscible materials. And I will later on get back to this kind of microstructures. Now we have created many more new microstructures since that time. So this is what I mean by metal composites, a combination of a metal, this is that white aluminum, and black graphite. Now, since 1969, there has been a tremendous growth in the use of metal matrix composites. So this shows that the volume of metal matrix composites used over the years has increased significantly. And right now, about $400 million worth of metal matrix composites are produced. The number of research papers in metal matrix composites has increased exponentially. And in 2019, about 300 papers were published. And this shows that the major uses of metal matrix composites are in ground transportation, that I will show later, thermal management in electronics, aerospace, industrial applications, and consumer products. And this chart shows that the different matrices in which ceramic reinforcements have been put in, and the biggest share is in aluminum matrix. And of course, all of you are familiar, but just to set the stage for my talk, metal matrix composites are a combination of metals and ceramics, and it could be either long fibers of a ceramic phase that we are showing here aligned, and this is a rendition of a ceramic fiber, and the white is the metal. So this is unidirectionally aligned long fiber composites, and many of them are used. We will not talk a great deal about them. And the second is that the fibers could be short and randomly oriented. And the third kind of metal composite where particles that are discontinuous, particulate shaped, disperse in the matrix of aluminum or any other metal, and the white is the metal, and these are the particles. And these particles could be angular as they are shown here. They could be spherical, they could be solid, or they could be hollow, or they could be micro or nano size. And I will later on show you that this ability to change the shape and size and solid or hollow, I could create a number of new applications for metal matrix composites. Now, metal matrix composites made by casting have been used for a long time. This is a picture of a typical aluminum silicon alloy, which is in all cars, everybody's cars, the piston and liners, silicon needles embedded in aluminum. And the second well-known metal composite is graphite, a ductile iron in which spherical graphite is dispersed in the matrix of iron. These two are phase diagram restricted composites where the amount of silicon and its shape and the amount of graphite particles is restricted by phase diagrams and thermodynamics. The composites that I will be talking about today where you can break the boundages of phase diagrams and add any particle to any metal as long as you can mix it. So that opens up the ability to create a lot of new metal matrix composites. And I will show you some examples here of metal matrix composites, some microstructures, including some from components that have been synthesized. The first picture here is sapphire. Sapphire is an aluminosilicate fiber. This dark sapphire fiber embedded in the matrix of aluminum by squeeze casting. And this has been used in Toyota diesel engines since 1985. The second microstructure shows 70% of particulate silicon carbide, this dark silicon carbide embedded in aluminum. And this is being used as heat sinks in all laptops, probably the laptop that you have in your lap right now. The other microstructure is where graphite particles are embedded in the matrix of aluminum. If you look at the phase diagram, there is no miscibility of carbon in aluminum. You should not have been able to produce this based on thermodynamics. But by introducing graphite particles into the melt of aluminum, we have been able to produce this particulate composite microstructure, and I will talk to you about this in later, that how it has been used to reduce friction and where conserve energy and environment. Another example where spherical alumina particles have been dispersed in aluminum matrix. Here is another example. 20 volume percentage of this angular silicon carbide are dispersed in aluminum, and I will show you this has been used for brake rotors in many cars to conserve energy and fuel. And this slide shows a variation of aluminum graphite composite, that how is in a single step you can produce a functionally gradient composite. So what we did, we took a melt of aluminum graphite, centrifugally cast it, so all the lighter graphite particle comes to the inner periphery, and this is where it can be used for a cylinder liner or bearing application. So it is a functionally gradient composite made by a very simple metal casting technique in a single step. And you can use this kind of technique to produce many other functionally gradient composites. You can make metal matrix composites by diffusion bonding or powder metallurgy, which are solid state, but they are much more expensive than the liquid metal technology that I will be talking about, where you add particles to liquid metal and then solidify. And this is the most versatile because you can produce very large castings, very complex shape or hollow castings that are not possible by other methods. And this shows a very simple schematic that how you will produce a melt of any metal, like it could be aluminum or magnesium or zinc or copper, and put a mechanical stirrer to stir it. And while you are stirring, you can add particles or fibers, micro nanoparticles, to create a suspension in liquid metal and then pour it in a mold, and it solidifies to produce a cast metal matrix composite. And this slide shows my industry partner, Eck Industries. They have upscaled this. In our research labs at the university, we produce maybe 20-30 pounds. This shows that this has been upscaled to 400 pounds. So you can produce very large batches of metal matrix composites and produce them. Here is an example of a brake rotor, a large brake rotor of a train used in Germany, and it is being poured. This is the melt of aluminum silicon carbide being poured in a sand mold to produce large train brake rotors, which are, as I speak to you, running in German trains to reduce their weight to conserve energy and the environment. Another method to produce metal composite is where you make a fiber preform or particulate preform and you infiltrate liquid metal. This is liquid metal, this is infiltrated in the spaces between the fibers, and you let it solidify to form a metal composite. This method allows you to incorporate very large amounts of reinforcements, up to 70 or 75%. And this is what has been used to produce the chips, thermal management chips in your computers. And this has now been upscaled where you do 3D printing of a ceramic preform, incorporate that preform in a mold, melt liquid metal on top of the mold, and apply pressure so the liquid metal goes, infiltrates the ceramic preform to produce a near net shaped casting of a metal matrix composite. So these kind of industrial processes are now available. I have only 25 minutes, so not much time to get into the scientific issues, but there are several. Transfer of reinforcements into the metal. We have worked out the thermodynamics and kinetics of this that allows us to calculate the kind of impellers and ultrasonic energy and pressure that you need to make these metal matrix composites. Movement of reinforcement in melts. Effect of reinforcements on viscosity and fluidity of metal melts and on the hot tearing tendencies. The effect of reinforcements on nucleation growth and microsegregation of solidifying matrices, and engulfment and pushing of ceramic reinforcements by solidifying interfaces. And of course, effect of distribution, bonding, volume fraction on the physical and mechanical properties. And as I said, I will not have the time, but I'll just give you a little feel for what kind of scientific issues are involved. So you see here that if you have a solid liquid interface here, it is growing with a velocity v sub SL, and it sees a reinforcement. Here, a spherical reinforcement. There are many forces that are applied on this particle. They would be gravity, they could be drag, and they could be just motion due to inertia. And there are two things that can happen, that this particle can either be engulfed by the solid liquid interface, or it can be pushed. And this has implications on where the particles wind up in the cast structure. This is what gives you an example that whether this is a solid liquid interface, whether the particle is engulfed or it is continuously pushed. And this is a very lot of scientific papers have been written, including our own. We have developed models to predict whether the particles will be engulfed or pushed. And I will show you the implications of this on the properties. As I said, we have extended this technology of metal matrix composites to now nanocomposite, where the particle size is nano size and a solid liquid interface approaches it. And in this case, in addition to the other forces, you also have to deal with the Brownian motion of the particle, and this influences whether the nanoparticle will be engulfed and whether it will be within the grains, because that will influence whether you get high mechanical properties or not. And this is a slide from our lab in University of Wisconsin, Milwaukee, where we are mixing nanoparticles of alumina in a melt of aluminum alloys using a mechanical stirrer as well as an ultrasound energy sonicator. Both these mechanical and ultrasound energies are able to disperse nano-sized particles of alumina, and after solidification, this is a TEM picture. You see 2 volume percentage of alumina particles dispersed in the matrix of aluminum. An example of how, using a simple mixing technique, you are able to produce a nanocomposite. And why nanocomposites? Because they can give you better properties than microcomposite, because the distance between the particles is nano size rather than micro size. Here is an example. I was talking about whether the particles will be pushed by the solid liquid interface or whether they'll be captured. And if they are pushed, all the reinforcements will be at the grain boundaries. It will not give you that much improvement in properties if they were engulfed and these nanoparticles were within the grain boundaries, within the grains. So that is an effect of whether the particles are pushed or whether they are captured. Ideally, you would like the particles to be captured and within the matrix and within the grains of the particles. Another effect of reinforcements on the solidification microstructure, this is an example where silicon carbide fibers, these silicon carbide fibers, you are looking at the cross section, they are embedded in an aluminum copper alloy. The bottom part shows where there are no fibers and the top part shows where there are fibers. And what this shows, that the micro segregation which is influenced, which is shown by the gradation of black colors, the micro segregation is much less when there are particles present during solidification. So you influence nucleation, you influence growth, and you influence micro segregation in a casting when fibers or particles are present in the matrix, and this has implications on properties. The next question is, why do we want to use metal matrix composites? And the reason is because it allows us to make parts in our transportation systems and in other systems much lighter, so that we consume much less energy in moving them and produce much less pollution to prevent the global warming. So this slide shows a plot of specific modulus and specific strength. The higher is the combination of these two parameters, the lighter is the material you can make, lighter the component will be. So you want to move along this diagonal in terms of properties. Most of the monolithic metals that we use today, the aluminum and steels, they are here. As you add microparticles, you move along this direction. So now you can make the parts much lighter. And if you add nanoparticles, it even moves more along this direction. So you make parts much more lighter compared to monolithic metals when you use composites. And that's the motivation for using these in transportation systems. This is another slide that shows how in the case of aluminum and magnesium, you have moved from monolithic to microcomposite and to nanocomposite, moving along this diagonal. Now, why do we use metal composites in thermal management systems? This is a plot of coefficient of thermal expansion versus thermal conductivity, lambda by rho. And in our thermal management systems, in our computers, we want the CTE to be of a given value so that CT is same as the chip. Only thing is you want the thermal conductivity by density to be as high as possible. And this is what you see here. Older materials like Covar or Invar are here, but when you make metal composites, you have much higher lambda by rho value. And this is why in all the computers, you use metal matrix composites as heat sinks. I did talk about that why in nanocomposites you get even better properties than micro. And this is a plot, this is a table that shows the properties you can get if you add alumina particles to aluminum. When the particles are micron size, the properties you can get are up to 148 megapascals. But if you reduce the size of alumina to nano size, you can get strengths as high as 500 megapascals, which is equal to steel. So you can get the same kind of strength as steel with much lower density, and that shows the power of metal matrix nanocomposites compared to monolithic materials. In order to help the environment and reduce the cost of metal matrix composites, my group has invented the use of waste fly ash. Fly ash is a waste byproduct. It is landfill, impairing our environment. And if you look at this fly ash, 80 million tons of fly ash are landfilled in the United States, and 2% of this fly ash is hollow. And this slide shows spherical, perfectly spherical hollow particles of fly ash, which is an aluminosilicate ceramic available to you for free or at no cost. We have used pressure infiltration to incorporate these hollow particles of fly ash in the matrix of aluminum, which is white. So this is a 60 volume percentage hollow microsphere embedded aluminum. We call this syntactic foam. And this syntactic foam has a density much lighter even than aluminum, about 1.4, and its energy absorption per unit weight is better than that of steel. So it has been used, it is being thought of to be used in cars to prevent the injury due to crashes and also for armor applications. And aluminum fly ash foams and other syntactic foams can be incorporated in hollow steel frames to produce lightweight frames for cars. In lead batteries, the problem is lead batteries are very heavy, and we have shown that we can incorporate hollow microballoons in the lead tops to reduce the weight of lead batteries. This is hollow microballoons embedded in the matrix of lead. One of the problems I have faced, they said, can you make aluminum cheaper? And this shows that we have incorporated solid fly ash particles which are available at no cost in aluminum to reduce the amount of aluminum in a intake manifold casting. This is an example of a filled metal made by MMC technology. We have extended the technology of metal composite to produce self-healing materials where if there is a crack, it can heal itself. And this is done by incorporating the fibers of shape memory alloy nitinol, which shrinks, remembers its shape in the matrix of aluminum. And when you stretch it, the aluminum fractures and you see a crack. If you heat it, the nitinol fiber, which is still intact, shrinks and it closes the crack. So in this metal composite, you can get self-healing of crack. And if you can see here, in this tensile bar, there is a crack. After heating, the crack has disappeared. So an example of self-healing metal matrix composite. Another application is that if in a tin bismuth, I have incorporated long fibers of shape memory alloy and I put in a bending machine, so the bar is bent and there is a crack in here. If I heat this, because of the shape recovery of nitinol, this bar, as you can see as I moved after 36 seconds, this bar has straightened and the crack has shut. So it shows the ability to produce materials with shape recovery and crack closing abilities or self-healing abilities. I have very busy slides that I will not try to read through, but in my full presentation and papers, you will see a number of major companies that have used components of many composite materials in pistons, engine block, brake rotors, cradles, missile fins, and so on. And the producers have been major international companies world over. At our university, this is a very busy slide showing that we have produced wear-resistant, lightweight, self-cleaning, self-lubricating, self-healing, high thermal conductivity, high strength and low cost metal matrix composites for a variety of applications in transportation and other applications that I will show you in a few minutes. This is just an old slide showing that discontinuously reinforced metals, means particulate composites, have been used in space applications as antenna wave mask for Hubble telescope. I'll show you a picture in a minute. And commercial LEO satellites or GEO ComSats for automotive applications as drive shafts, cylinder blocks, brake rotors by Chevy, Toyota, Honda, and Plymouth. In aero propulsion, in Pratt and Whitney engines, in fighter planes, in thermal management applications in Motorola power chips, and also in recreation, bicycle frames, brake fins, and golf clubs have been made out of metal matrix composites. A little busy slide of many aerospace applications where MMCs have flown, including F-16 aircraft, Pratt and Whitney engines, and this is the Hubble telescope antenna here. This was aluminum carbon, now it is aluminum silicon carbide. The struts of orbiter, they were boron fiber reinforced aluminum, and these are the applications of MMCs in helicopter areas. This is a slide of use of metal matrix composites in automotive applications to reduce energy. Motorcycles, brake rotors, these used to be cast iron. By making in metal matrix composites, they will be 65% lighter and therefore conserve energy. This is a drive shafts of aluminum silicon carbide, and I did mention German trains which have got aluminum silicon carbide brake rotors. This is a cylinder block in which you see here a section of the cylinder. Fibers of carbon and alumina were embedded in this cylinder block, and this allowed you to reduce the weight and the size of cylinder block and reduce the energy. And this has been, this is a block from Honda Prelude which ran for many years. Another picture of different uses of metal composites. This is an engine pulley that is made of metal composites, a brake drum of a large military truck, motorcycle brake rotors, automotive brake rotors. This is a compressor that we developed in our lab for truck air brakes. This compressor used to be cast iron, but now we have made it in aluminum, and the liner is aluminum silicon carbide, and it reduces the power consumption in compressors, and it improves the compressor efficiency. A slide of many investment castings made of metal matrix composites by O'Fallon Corporation. These are examples of many aluminum graphite composites that I have made over the years. A piston that reduces fuel consumption, a cylinder liner run by Associated Engineering Company in a Formula One race in a Ferrari, and even though there was a failure of the radiator, they were able to complete the race. A real example of use of self-lubricating aluminum graphite composite in a high-performance cars. The small end of a connecting rod, instead of expensive leaded bronze, we use aluminum graphite and showed that it works. This is for a small engine like lawnmowers. A aluminum graphite cylinder liners encapsulated in a pressure die casting under industrial conditions, and this showed that it reduced the fuel consumption in small lawnmower engines. Another example of centrifugally casting aluminum graphite encapsulated in a small diesel engine, and it showed reduction in fuel consumption. In addition to adding one reinforcement like graphite or silicon carbide, there has been development of incorporating more than one reinforcement, and this is an example where graphite and silicon carbide, the black is graphite and fine silicon carbide is here, and this hybrid aluminum silicon carbide here is better microstructure, graphite and silicon carbide. This has been successfully cast as cylinder liners, and this table shows that how the properties, the strength and thermal conductivity of this hybrid metal composite are better than cast iron, aluminum silicon alloys, Nickel coated aluminum alloys, and so on. And these liners, Intelligent Composites has tested in small engines, in watercraft engines, in motorcycle engines, and hopefully they will be used in automotive engines to reduce energy consumption. I will briefly, before closing, talk about some of the research imperatives, because I'm talking about future imperatives. So there is still a lot of fundamental research that can be done after the first 50 years. And I want to challenge the younger material science people to kind of address these problems and solve, so metal matrix composites can be used on a more wider scale to reduce energy consumption and reduce global warming. What are some of the problems? Preventing agglomeration and clustering of nano and micro reinforcements during synthesis and casting of metal matrix composites. Reducing the cost of cast metal composites through low-cost reinforcements and in situ produce metal matrix composites through low-cost processing. Developing property database to design components in metal matrix composites instead of wrought materials or monolithic materials. Developing supplier base and capability to cast large number of cast metal matrix composites. Many auto companies, if they even want to use MMC components, there are no large supplier bases. Development to recycle metal matrix composites. Developing ultra performance metal matrix composites reinforced with graphene and carbon nanotubes. These can have much higher properties in metal composites than have been achieved to date. Large scale and long-term performance testing of metal matrix composites for different applications, including cylinder liners, pistons, connecting rod, compressor scrolls, housings, rotary engine components, and so on. And then we need improved theoretical models to improve structure processing property relationships in cast metal matrix composites to understand formation of cast structure during solidification of castings. And really this is a summary. As I said, starting from the initial synthesis of cast metal composites reported in 1969, of which I was a part, the metal matrix composite industry has grown to several $100 million at this time. And in view of the need for lighter weight material components, which can conserve energy and save the environment, the demand for MMCs will grow. Major barriers of the growth of cast metal matrix composites include high cost, lack of design data, difficulty in machining and recycling. Several components including brake rotors, calipers, heat sinks, cylinder liners, recreational equipments of metal matrix composites have been manufactured and used in actual applications. And composites cast today have a very large list is there, but they include aluminum silicon carbide, aluminum alumina, aluminum graphite, and aluminum fly ash. And several conventional casting techniques, which are low cost, including sand, investment, permanent mold, squeeze, centrifugal, and ablation casting, have been used to cast metal matrix composite components. In addition to microcomposites, recent work has been directed to produce metal matrix nanocomposites, syntactic foams, self-lubricating, and self-healing castings. Thanks very much for your attention.